Hello and welcome to another tutorial. In this tutorial I'm going to finish up our discussion on root finding algorithms. So one last thing that remains from root finding algorithms is the generalized Taylor's method, and it's based on two facts. Fact one is that it is easy to find the roots of a polynomial, and we have general methods such as Laguerre's method that can provide all the roots of a polynomial. Okay, and fact number two, any smooth function can be expanded into a polynomial about a given point. Okay, we've seen that. We have implemented the Taylor expansion in Java before, so if you're not familiar with Taylor expansion, you can just look at one of my tutorials on the Taylor expansion method and its implementation in Java. So how does the generalized Taylor's method work? It works based on a few steps. Step one, find Taylor expansion at an initial guess of the root over a given interval. Okay, so if you have an interval and it's a valid bracket for the root, then you can pick one point, for example the midpoint of the interval, and then find the Taylor expansion of some degree, first degree, second degree, third degree, at that point. Okay, and then yes, obviously we assume that the initial interval brackets the root, and then after finding the Taylor expansion, which is a polynomial, find the x-intercept of the Taylor polynomial, which is another way of saying find the real roots of this polynomial. Okay, and then because we're interested in the roots in the given interval, only keep the real roots of the polynomial that lie in this interval. Okay, and then perform a recursion by finding the Taylor expansion and the new x-intercept. So find the real roots in the interval, and then we also have the start and the end of the interval and all the roots in between. So find the valid bracket again, and then in that bracket do the recursion. So pass the start and end point of that bracket, that new bracket, based on the roots of the polynomial to the function, and then it automatically goes in, creates the Taylor expansion, find its real root, and then continues until it finds the root. Okay, so if we have a Taylor expansion of 1, which means at each point, at each step, we're finding the tangent line to the plot, to the function f of x, and then finding its x-intercept. This is exactly Newton's method. So you can imagine that if Newton's method, which is basically the very special case of degree 1 Taylor expansion, has a quadratic convergence, higher order Taylor expansions can have much faster convergence. Okay, and now obviously if we want to do Taylor expansions of more than first degree, second degree, third degree, we need to have or calculate the higher order derivatives of the function, second derivative, third derivative. So one way is doing the numerical estimation. We looked at how to calculate the first derivative numerically, but there are also expressions for calculating the second derivative, third derivative, etc. Right? But there are also other ways. One way is to use the real root deriv function interface that we implemented. This forces the user to not only give the expression for f, but also the user should also give the expression for f prime, f double prime, etc. Because if you recall, real root deriv function returns an array of double values. The first one is the f, the second one should be f prime, the third one should be f double prime, etc. So that's one way. So the programmer asks the user to actually provide these functions f prime, f double prime. That's one way. The other way is to use our symbolic function space that we developed in some of the previous lectures. and then we can construct the function from the basic functions, and the basic functions have analytic expression. So that's another way of finding all the higher order derivatives. Okay, now besides all these ways of the ways that we discussed and implemented all these root finding algorithms, there are also other already available libraries that you can use to find the roots. You don't need to write all these algorithms by yourself, which I highly recommend you do that. So just follow my tutorials and try to implement and even improve all these root finding algorithms. Okay, but if you don't want that, if you want to just use already available libraries, which are good libraries, one of them is from Michael Flanagan's Java Scientific Library. We discussed this before in the polynomial tutorial and also in the complex numbers tutorial. So you can find it, you can find the Java archive file and download it from Michael's website, www.ee.ucl, University College London.ac.uk/m/Flanagan/Java. And there is a complete Java document on the website with all the explanations of all the methods and all the classes and all the packages. Okay, now this is a snapshot of how this Flanagan library looks like. So it has a couple of packages, and one of them is called roots, and in this roots it has 3 classes. 2 of them are interface, and one of them is the main class that implements all the algorithms. And it's exactly similar to what we already developed so far during all these lectures. So it has a real root class, which is an interface, a functional interface, and defines a real valued real function. So you supply a real double value and it returns a double value for the function. And there is another function in functional interface, real root deriv function. So this has a deriv in the name, real root deriv function, exactly like what we implemented. And it basically defines the function and all its derivatives. So it returns an array of double values. Finally, we have a real root class that again implements all the basic algorithms, bisection, Brent, Newton-Raphson. And there is another method that it implements. It's called false position method. And if you look this up, false position, on Google or go to Wikipedia and search it, it's basically our improved secant method. So that's another name for improved secant method, false position. All right. So the structure of roots package in Michael Flanagan's library is exactly the way we implement it. Now, regarding the false position or the secant method, just to refresh your memory, if I go to the secant method, when we discussed secant method, I mentioned that the original method is a recursion that says that, okay, start from x0 and x1, which should be a bracket of the root, and then connect the line, connect the two start point and end point on the function, and the x-intercept, or the point that it crosses the x-axis, is guaranteed to be between x0 and x1. Okay. And then the idea of the recursion was that now take x1 and x2, the new crossing, as the new interval and continue to find the x-intercept. The problem was that if you just do this simple recursion, the x1, x2 might not be a bracket for the root, which we see it here, right? So the idea of the improved secant method, which is also called the false position method, is that instead of doing the recursion like that, be some intelligent, and instead when we find a new crossing point, xn, test for the bracket, test whether or not xn x minus 1 is in fact a bracket or not. If it's not, then xn x minus 2 is the bracket, and we should connect them instead of this line. and this also guaranteed to fall between xn minus 2 and xn. So we're getting closer and closer to the root. Okay, so it just says that be more smart about the way you implement the recursion. All right, now there is another a good point or a good algorithm in this real root class, which also basically allows for automatic extension of the original interval. What does it mean? It means that if we set the original search interval as a b, it finds the half length of the interval b minus a over 2. Okay, now what it does when we call one of these methods is that it tries to first determine whether or not this initial interval is a valid bracket or not. If it's the valid bracket, then it continues with the method, but if it's not, it tries to extend the interval, the ab interval, into a minus dx, b plus dx. Okay, so it adds half the interval to the lower bound and upper bound, and there are flags that you can set whether or not you want to extend the upper bound, lower bound, or both of them, or none of them, and we'll look into that. Okay, so that's another interesting thing that we can implement and try to extend the bounds of the initial interval if it's not a valid bracket. So let's head to Eclipse. Let's try to decompile this real root class and look into all the methods. So if you go to my mathlib library and go to the reference libraries, we have the Flanagan.jar. In the Flanagan we have the roots, and in the roots we have real root function, which is a functional interface, has one abstract method function, and it takes a double value and returns the value of the function. Okay, and we also have real root deriv function, which returns an array of doubles. So the 0th element is the value of the function, the first element is the derivative, first derivative, the second element is the second derivative, etc. Okay, and then we have the real root. Now in the real root we have a couple of private fields. One is originally the root is double.nan, exactly like what we did. We have some tolerance. This is I believe it's used for the convergence. We have maximum number of iterations, and iter n, which I believe is used for the number of iterations in the Newton's method, and then upper bound and lower bound of the search, the estimate of the root, maximum bounds extension. This is this determines how many times, the maximum number of times that we can extend the bounds. No bound extension, this is a flag that if we set it to true, the methods don't try to extend the bound if the original interval is not a valid bracket. No lower bound extensions, no upper bound extensions. So if we set one of these to true, then only one of the bounds of the initial search interval is extended. Suppress limit reached method, return nan, which we said it's a good idea to always return nan. Suppress nan message, a static iteration math. So this is basically, not only it has all the methods, it also implement them as static methods. You see Brent static, bisection static, false position static, NewtonRaphson static, and also the roots of the polynomials. Okay, so it's also always a good idea to implement the methods as static methods. Then we can directly access them and pass any function. No static bound extensions, no static lower bound extensions, no static upper bound extension, a static return nan, real tolerance 1 e minus 14. So this is the actual or real tolerance that it uses to see whether or not the root has been found. If you recall, we set it to 1 e negative 15. So here it's set to 1 e negative 14. So there are some setters for all these, most of these parameters: set lower bound, set upper bound, reset nan exception, to true, resend NaN exception to false, suppress NaN message, suppress NaN message, and allow NaN message, set estimate. So you can just use this to set the global estimate of the root, set tolerance, get tolerance, set iteration max, get iteration max, get iter n, set maximum static bounds extension, no bounds extensions, no lower bound extension, no upper bound extension, suppress limit reached method, suppress limit reached method, Brent. So this is where the algorithms start. So the first one is Brent method, which takes a real root function and then calls the general Brent method that has a real root function and the start point, the start of the interval, and then the end of the interval. So var2 is the start of the interval, var4 is end, and var1 is the actual real root function. Okay, so when we call this, it sets the lower bound to var2, upper bound to var4, and the first test here is whether or not the upper bound and lower bound are equal. And as I mentioned before, the exact equality is not recommended with double numbers. It's always best to compare them with the tolerance. But here it's using exact equality, and if the start and end of the interval are exactly the same, it returns or throws an exception, illegal argument exception, and says that upper cannot equal lower. Okay, so this is the first test that we should do. The second test is here. So if the var2 and var4 are not the same, then it tests whether var2, which we assume to be the start of the interval, is in fact less than var4 or not. So if var4, which is the end, is less than var2, it just swaps the values of the var2 and var4. Okay, so it just ensures that the start point is always less than the end point. Not equal, it's not equal, and it's always smaller, which is really not required for bisection or trisection method, but for Brent, it just tries to make sure that the start point is less than the end point. Okay, if it's not, it swaps the values. So var7 is just a intermediate variable here that first holds the value in var4, and then we copy var2 to var4, and then copy var7 to var2. This way we swap the values of var2 and var4. Okay, so this is the second test, and then it finds the values of the function at the start point and the end points. var9 and var11 are the function values, and then tests if one of these values is NaN, which most likely is not going to happen for our functions, but in a rare case that the function actually returns the NaN, it tries to catch this and returns a message that, okay, function is NaN, I cannot do anything, I cannot proceed, so it just returns NaN as the root. Same thing for so this was for the lower bound, and the next is the upper bound. The function at the upper bound is NaN. Okay, next it tries to find the half length of the interval. var15 is var4 minus var2 over 2, so it's the half length, and it sets the flag var3 to true, and var3 is basically for the flag for extending the lower bound and upper bound. So it finds half length, this flag is true, so it goes into this while loop, and then it tries to look at the bracketing. So var9 is the function value, var11 is the function value at the other end. So if the function value at two ends is less than or equal 0, it's in fact a valid bracket, so it sets the flag to false, which means then we just come out of the there is no need to extend the bounds, okay, of the interval. It just sets the flag to false, and then the while loop terminates. But if it's not a valid bracket, so if var9 times var11 is greater than 0, it tries to extend the bounds, lower bound and upper bound. So if no bound extension flag is set to true, it says that okay, I cannot extend the bound and the current interval is not a bracket, so just return that. But then if this is basically false, so we allow for the extension of the bounds, then it increases this integer variable, which is 0, which keeps track of how many times the bounds have been extended, because we have this variable maximum bounds extension, which I believe originally was set to 100. So if we haven't reached the maximum number of bound extensions, then what happens, it subtracts the half length of the interval from the var2 and then updates the value of the function at the new lower bound. Similarly here, it adds the half length to the endpoint and updates the value of the endpoint and updates the value of the function at the new endpoint, and then the while loop continues. So this is this whole thing, this whole while loop is for extending the bounds in order to get a valid bracket. Okay, and then now it gets the valid bracket. Then it has two other tests. One is the value of the function at the start point of the bracket and the value of the function at the end point of the bracket, and it tests whether or not the start point and the end point is in fact the root. If it's the root, it sets the root to the value and then basically returns. Okay. Now, if you recall, we in fact implemented this as one of our stop conditions. If we go back to our roots, to the real root, for example, for bisection, we had this. We checked for the value of the function at the start, less than absolute error. And again, it's not recommended to use exact equality with double numbers. It's better to have a tolerance, which we define as absolute error. But then we also looked at the relative error, because eventually the iteration creates a sequence of numbers that we hope to converge to the actual root. And for the bisection, it is guaranteed to converge, but it's pretty slow, or it could be slower than the other methods such as Brent or Newton. Okay, so these two tests, let's say these two tests fail, so the start point and the end point of the interval are not the roots, then it goes into the iteration. So what it does, it finds the midpoint as the guess, and then finds the function at that value of the function at that point, and then does the iteration. And this is how it implements the iteration for the Brent method. So a start point, end point, and we need another third point, which was our guess, and here it's set to the midpoint. And while var6 is a flag that sets the termination of the Brent's algorithm. So if it goes into this recursion, the first thing that it tests is the stop condition of the recursion. The stop condition happens when as long as the value of the function var23 is basically the value of the function. As long as this value is larger than the tolerance, we continue, and then here is where we actually do the quadratic polynomial interpolation, and it continues until it terminates, and after that the root is set, and there are also other flags, other checks for the maximum number of iterations, and eventually it returns the root. So as you can see, this is not exactly the way we implemented Brent's method. We just so here it's not using the recursion in its method calling way, right? Calling the method again and again creates a stack of methods in the execution chain. But here it just puts everything in the while loop and updates the values of the variables instead of calling the method over and over again. So if you recall, for example, in the Brent method that we implemented with the start and end and guess, we just go into the Brent again and again. So this creates a stack or a chain of method callings, and eventually once it terminates, it comes back up. So this, when we use recursion, it makes the code much cleaner, but we have some performance hit because of this chain of method callings that we have to go deeper and deeper and then coming back. So while loop could be in fact more efficient, but it makes the code a little bit more complicated and longer. Okay. Now after Brent, we have the bisection method, which is the most simplest. So we have the function and the start point and end point. Obviously, the first test is checking for the lower bound and upper bound being equal, which is not allowed. And then we test whether or not the start point is in fact less than the end point. If not, we just swap the variables. We swap the values. And then we have the same thing here, value of the function at the start point, var9 and var11, value of the function at the end point. If one of them is none, we return none. And then we go into the while loop for extending the bounds, a lower bound, upper bound, and after that we check whether or not the start point or end point is the root. If not, then we go into the bisection and the binary search. And the binary search is basically this part. So var23 is the flag for checking when to end the iteration, and then when var7 is less than tolerance, we just call var24 as the root, and initially the initial guess is the midpoint, var2 plus var4 over 2. It's the midpoint of the interval, just exactly like we did. We said that, okay, the initial guess is the midpoint of the interval. Okay, so this is one condition for termination. The other one is that once it does that, var24 and then it checks for the brackets, and this is the recursion. So what it does is looks at the looks at the var21, which is the value of the function at the midpoint, and check it by the value of the function at the end point and the value of the function at the start point. Okay, so if this is not a bracket, it sets the var4 to var24, so it goes into the second half, and if it's true, it goes into the first half, and just it continues, var24 var2 plus var4 over 2, and eventually this way it does the recursion or the binary search. And again, using the direct method recursion, so basically it does exactly this. So it looks at the two brackets, start to the midpoint, at the midpoint to the end. One of them is the valid bracket, and then it goes does the recursion in that bracket. As you can see, our code is much cleaner and readable, but it uses the method recursion, which has this stack of the methods and has some performance hit because of that. Next is the false position, which is our secant method. Again, the same test for the equality of the lower and upper bound, swapping the values for extending the bounds, which is this while loop, and then checking the initial and end points as the roots, and then the actual secant implementation. And in the secant, let's bring up our code. We have the start and the value of the function at the start and the value function at the end, and then we find the inverse of the slope of this line that goes from the start to end, and then we do the recursion. Okay, here's the same thing, var4 minus var2 divided by var11, which is the value of function of var4, and var9, which is the value of function at var2. Now this implementation is a bit different because here it uses the plus sign, but if you look into the details, eventually this is equivalent to what we did here. Now the reason it tries to implement it in this way, because then we avoid the case where this denominator becomes 0, because the only way that this denominator can become 0 is when both of these absolute values are 0. But if one of these is 0, we already have these checks for termination. So if this checks fails, means that this denominator is never 0. So this could be a better or safer way of implementing the secant method. And this continues until it finds the root and returns the root. Now there is another method here called so we have the Brent, we have the false position, we have NewtonRaphson, and again the same story, checking for the start point and the end point, and then doing the extension of the upper bound and the lower bound, and then eventually finding the root. For the NewtonRaphson, the root happens here. Basically it finds the slope of the function, so it calls the real root deriv function. It assumes that the user has already provided the function with the value with the derivative function too. So var9 here is the var11, so this is var11, and var11 is basically the 0th element is basically the value of the function, the first element is the value of the derivative. And if you recall, in the recursion of the Newton's method, we have the previous value minus the function divided by the derivative of the function. That's why we have var11 0, which is the function, divided by var11 number 1, which is the derivative of the function. And then it checks whether or not the value of the function is in fact 0. If it's not, and then the okay, and then it updates the value, the iteration, which so it finds this fraction, this number, and then subtract it from the original point, and then substitute it in that variable. So var1 is the variable that is keeping track of our iterations. Okay, so basically it calculates this, subtracts from the number, and substitute it into the number itself to be able to do the iterations. So this is where the actual iteration happens. And if you recall, in our method, the way we implemented Newton was to call the Newton method again with the updated value. If you don't want to do that kind of method recursion, you can just simply do this with a while loop. Then you must have a while loop so that you can set a flag var7 for termination. Okay, Now there are also other methods. Bisection Newton-Raphson, which tries to combine the bisection. Basically, you give, instead of having a double value as the initial guess, you give the start point and the end point. So it runs the bisection first to find the valid. Basically, the idea here is like this: the bisection Newton-Raphson is, you give the start and end point of the interval, and it tries to run the bisection first to find a bracket for the root. Once you have the bracket, it goes into the Newton iteration. Okay, so it's a combination of bisection and Newton-Raphson. And there are also some other methods for setting some of the other global variables, and then all these methods, Brent, bisection, are also implemented as a static method. So these are class level methods, and you pass the real root function, and then for Brent, for example, we need 3 points, and it basically copy and paste of the previous methods, but here these are static methods, so we can directly access them with the class name. Bisection, we have 3 points, start, end, and the initial guess. False position method, we have 3 points. Bisection Newton-Raphson, we have 1, 2, 3. Newton-Raphson, we have 2. And then it also has methods for polynomial, so quadratic polynomial, and these are the coefficients. var0, var2, var4 are the coefficients of a quadratic polynomial, and it returns the roots and also mark them with complex or real. And basically what it does is, for quadratics, it's very simple. It calculates the delta function, and then basically the discriminator of the quadratic equation, b squared minus 4ac. var2 is b, var0 is a, and var4 is c, and checks whether or not it's negative or positive. If it's negative, we have 2 complex roots, and it calls the complex polynomial to find the complex roots. Otherwise, it just finds it's just the basic algebraic math, and all the roots are real. The same thing for cubic. It calculates the discriminant of the cubic polynomial and tests whether or not it has complex roots or not. If it has, then it calls the complex polynomial object and calls the cubic method. Otherwise, it just directly implements the algebraic equations for the roots. And there are also other methods for polynomial, roots of polynomials. You give an array of coefficients and an initial guess. Yeah, that's it. So this is the roots package in Flanagan's library, and these are very good methods. I highly recommend them and recommend that you use them. I also recommend that you follow my past tutorials on root finding algorithms and try to implement your own libraries. That gives you more flexibility in terms of modifying them, improving them. So this is the conclusion on for now at least, it's the conclusion on all the root finding algorithms. Next, we are going to look into some optimization methods. Thank you for watching, and I'll see you in the next video.